let's continue our lecture. And here I'm going to provide just a quick summary of what I told you yesterday. So it seems that there is an established correlation between neutrino source position and the brightest in radio blazars. Now about radio and gamma flares, that's actually a controversial question. As you know, the first strong association of blazar with the neutrino source has been established for TXS 0506, and exactly by coincidence of gamma ray flare together with high energy neutrino signal arrival. However, it seems now, after more observations, more detected events, that we don't always, and actually I think in less cases, we see gamma ray flares in blazars which we do associate with neutrino sources. But probably the connection with flares and brightness in radio is more relevant right now. However, it's it's a new science, so we don't know yet. I just wanted to mention what is discussed in astrophysical community. So AGN, we understand now that AGN is a supermassive black hole which must have a high spin with accretion disk bringing magnetic field, and only in this case we can have an activity, a working central engine and a powerful jet launched. Jets are outflows of both electromagnetic and kinetic plasma energy. And we also understood that at the jet basis, the Poynting flux dominates, so the energy is carried mostly by the electromagnetic field, which is amazing. In fact, only after traveling like tens of parsecs, plasma starts dominating. The bulk motion is observed directly in jets. Although we do not know, of course, we observe the bright features. Those can be some shocks going along a jet, or we really observe the plasma velocity. So at least shocks or plasma have relativistic bulk motion with detected Lorentz factors up to 100. The velocity is mainly poloidal, meaning along the jet, although there is a toroidal component, which is also actually observed. I haven't put a picture here, but we have a nice picture again for the most nearby jet. It's M87, where we can actually see the jet rotation, the rotation of plasma in a jet. And the motion is very well described by our familiar formulas for velocity of charged particle in crossed electric and magnetic field. Well, about the field configuration. Outside the light cylinder, and I must remind you that light cylinder has scale of about 10 to the minus 4, 10 to the minus 3 parsecs, while typical jet width in the parts on parsec scales is about 1/10 of parsec. So outside the light cylinder in AGN frame, toroidal magnetic field always dominates the poloidal component. However, in a plasma proper frame, it may be different, and when the jet has just started accelerating, just accelerates, then in the plasma proper frame, poloidal component dominates, and when plasma reached almost its maximum velocity, then even in plasma proper frame, toroidal field also dominates the jet. Now let me just remind you some very basic equation, some very, not equation even, some basics for synchrotron emission. So what I was telling you, actually it was, let me turn back. So what I was telling you about what we may learn from MHD modeling of jets, about magnetic field, and the same MHD modeling actually provides us with total plasma number density. But what does shine in a jet? The plasma in jet, which we account for in magnetohydrodynamics, it may be cold, so it just moves with the bulk velocity, have zero rotation around the local magnetic field, so it wouldn't emit. So in order to have emission, which we actually observe, and here is the picture of M87, or again, it's a very nice picture obtained at 15 gigahertz. So here is the scale. This one is 1 parsec, but since it's in the picture plane, what we see, this part of the jet, the very beginning, elongates about 6 parsecs. So we obviously see an emission right here decreasing along a jet. And in order to have this emission, we need to have some plasma being heated, being relativistic to rotate around the magnetic field and to emit. So we have relativistic plasma, we expect. We have magnetic field, even in a plasma proper frame. So we must have a synchrotron emission, which for relativistic plasma is highly boosted. Here I like this picture. This is just a classical dipole emission diagram, and when you start moving your dipole, for example, along this line, this emission is boosted due to light aberration effect. And you will have such a pattern with a half opening angle classical of this order. Or if you move your dipole in this direction, you will have such a picture of emission. So you can see that first of all, emission is concentrated in a very narrow angle. So just imagine, for bulk Lorentz factor 100, it's quite a narrow angle, and it's also hugely boosted in intensity. That's why actually blazars are so bright, and that's what allows us to see blazars from very far distances. So by the way, which picture will be for synchrotron emission here? For synchrotron emission in jet, the B1 or the D1. So let's see. The acceleration is directed here. So for a particle in a magnetic field, it's directed towards the center, right? And the velocity, it moves in a circle like here. So it's this picture. Okay. Anyway, what we assume that somehow the total plasma number density, or prescribed by MHD solution and needed to launch a jet, or some part of it is somehow heated to relativistic speeds. Now, how it is heated, we will hear on the last 2 days by Evgeny Deroshev lectures. I guess at least some of the models. But we here assume the power law energy distribution for emitting plasma. Now, I will remind you that by stars I designate the values in the plasma proper frame. Here is dN, it's plasma number density, and Ke, I will use it extensively later. Ke is an amplitude of this distribution. So if we have a power law distribution for some part of plasma or total plasma number density, then we can try to understand what we see, how the jet shines. In this case, I will remind you that we introduce specific intensity, INU, which actually its best definition is provided here. It's an energy emitted from the unit area at the unit time through the unit solid angle and at unit frequency range. For this specific intensity, we write the radiative transfer equation, which is written along a line of sight. So when we solve such an equation, we just divide our picture plane in small pieces and calculate the specific intensity for each point along a line of sight. It's convenient to write it in plasma proper frame just because these coefficients are easily written there. So this is the radiative transfer equation. S is just a distance along a line of sight. So in whatever frame you define it. The right-hand side, this is a phenomenological equation. So the right-hand side consists of emission coefficient, J nu, and the second term defines the absorption. So if your medium does not absorb light, this is zero, and you see that along the line of sight, intensity just sums up due to this emission coefficient, due to emitting media. On the other hand, if you do not have any emission, probably you have some background specific intensity initial going through your media, then you see here you will have absorbed photons, and your specific intensity obviously will be fallen as exponent to the power minus minus alpha s. And you can see from this that alpha s is just an optical depth. So this absorption coefficient multiplied by the length provides you with an optical depth. So here is the emission coefficient. Some constants, here some constants. This function A of P, it's a function of your index of power law distribution, and it is known, it's just some composition of gamma functions. And here we have plasma number density amplitude, cyclotron angular velocity, frequency, and the emitting light frequency. So this is the expression. Here we have expression for an absorption coefficient. Again, some composition of gamma functions, constant, classical radius of electron, constant, C over R naught, plasma density, magnetic field, frequency. This result has been obtained by Ginzburg and Sarovatsky in 1965, And actually, it's a shame, I have never seen the derivation of these coefficients in any literature. So if you know, please tell me. You always have to look up in this paper or in some follow-up papers. Well, these functions can be tabulated. We can see the order of them. So finally, what we have? Just let me return. Okay, let's look at the absorption coefficient because it's quite important. You see that for a given plasma number density and magnetic field amplitude, the higher the frequency, the lower the absorption, and vice versa. So, solving the radiative transfer equation, here is the solution. It's a specific intensity as a function of frequency. Also in the plasma proper frame, just stars are emitted. We can see the following classical pattern of synchrotron emission of an ensemble of particles whose energy is distributed by any power law. So for high frequencies, the absorption is small, is low. So the bunch of plasma we are looking at is actually optically thin for us, and its intensity falls with the frequency. That's because the emission coefficient is also inversely proportional to the frequency. Okay, so it's falling, and the particular power index here depends on the power law distribution, energy distribution of emitting and absorbing particles. There is some point when the intensity reaches its maximum, and more or less it coincides with the frequency when our bunch of emitting and absorbing plasma obtains an optical depth equal to unity. So this is a maximum for specific intensity, and then as the frequency falls again, our source becomes optically thick, and we see the constant slope of this dependence 2.5, and it does not depend on the plasma energy distribution index. So this is a classical picture which we actually think is valid in radio emission of jets. It's supported by observations. Usually, when we measure spectrum of a jet emission, we measure specific intensity and some power proportional to nu minus alpha. So in some papers you can see either index here, p, or it is interchanged for index alpha. So that's the same thing. Now, this is just a very short slide. This is again a famous picture for M87. It's quite recent. It was obtained by the multi-wavelength Event Horizon Telescope program, which compiled, not all of it obviously obtained by EHT, because we can see many satellites working here, many programs working here, but compiled. So we see here the picture of M87 galaxy from 1000 gigaelectron volts, so it's gamma, going with lower and lower frequencies, This is Hubble, so it's about optics, going lower frequencies. And at high frequency, we see the black hole shadow, and for even lower frequencies, we just can see the radio jet. And this emission is just probably this emission safely is a synchrotron emission, which I reminded you of a few slides before. Here is the, well, more or less typical spectral energy distribution of an AGN or a blazar. It's SED, spectral energy distribution of TXS0506, compiled in this paper. And you can see, what can you see in the spectrum? Here is the low energy bump and high energy bump. And the total jet emission, the total jet AGN SED is modeled as follows. The low energy bump is very well described by the synchrotron emission of relativistic plasma. So here it is, and here the radio range. For high energy bump, there are several models. One of them is so-called synchrotron self-Compton or inverse Compton. Here it means that the same population of relativistic electrons which produced a synchrotron emission, bright and radio, they upscatter the same synchrotron emission up to higher energies. So hence this bump. Another possible component, we have of course some external jet emission like X-rays from or infrared from inner parts of accretion jet. So we can have external photons, also Comptonized, upscattered by the relativistic plasma in jet. So it is an external Compton, and maybe this bump may include some part of a synchrotron from protons, which has much higher energies. So this is a classical spectrum, and here is the picture I took from Plavin et al. 2021, which somehow depicts the emission of relativistic jets schematically. That's cartoon. Here are leptons, electrons, positrons. They emit synchrotron emission, which we detect in radio. They are being Compton scattered, so they used here only internal Compton, depicted here internal Compton. They synchrotron emission is upscattered, and we observe them as X-rays and maybe up to actually gamma rays. And then we suppose that there might be protons which produce pions and via cascade gamma rays and neutrinos. So this is a scheme for our jet emission, including from radio to possibly neutrinos. And here is the picture that shows us the following. The gray dots are all blazars. Blue circles here are the areas from which the high energy neutrino signal has arrived. And by colored stars are depicted the most bright blazars, most bright in radio. So this picture actually has established statistically some coincidence of bright blazars quite many intersections with the areas from where neutrinos come from. Why blazars? This is a nice unification picture for different types of active galactic nuclei, and what we are talking called blazars. They are BLACs and flat spectrum radio quasars, and those sources are AGNs at which jet from which are almost pointing directly at us at very small angle. Which means actually that the jet emission is so highly boosted, so powerful, that in case of BLAC division, we even don't see any lines from such AGN. And for flat spectrum radio quasars, we see some lines, but still the emission is highly boosted towards the observer. And by the way, this what makes us believe that it is the blazars out of all the classes of AGNs that are sources of neutrinos. Why? So they point at us. So the closer the jet exits to a line of sight, the brighter and more variable emission we observe. The main thing is brighter. So we see more photons going towards us. And if there is an event of neutrino production like flare, then the neutrinos, having almost zero mass, will be going into the same, will be boosted in the same way as photons. So we just will have a high probability of detection of such neutrinos. Because they are boosted, they will have higher energies. And higher variability just means that probably we must, if we want to prove that blazars can be neutrino emitters, then we must be looking for a highly variable bright blazars. So here is one point. Another point I have already told you. And of course, this nice picture does not explain everything that we observe, because I mentioned yesterday NGC 1068 is supposed to be a Seyfert galaxy, and it lies about here. And so probably it's not a blazar, and that's a big question how to put it into this picture. So returning to our to the main topic, I wanted to draw your attention to introduce it to you, is the effect of a core shift offset. Now, this is a very nice picture taken from this walk. Here we see, here we see a black hole, probably with accretion disk, some schematic jet propagating from the black hole. So at the very beginning, at the very base of the jet, it is quite narrow, and so the magnetic field and the emitting plasma density are high in this part of the jet. As the jet propagates, it widens. The amplitude of magnetic field here and the amplitude of emitting plasma number density decreases. So obviously we have the different optical thickness conditions in here and in here. So let's look at this picture. We see that the higher frequency, the more optically thin jet. And just recall that both absorption and emission coefficients are proportional to emitting plasma number density and magnetic field. So let's look at the most low frequency. It's like 1.4, typical frequency, 1.4 gigahertz. At this frequency, the jet becomes optically thick very far from its base. Just because the magnetic field, so here we are. Just because the magnetic field and emitting plasma number density are low. So what we see in the pictures, this part at the low frequency we see as the jet base. All this is just forbidden. We don't see it. It's optically thick. Then, if we look at the same jet at some higher frequency, like 5 gigahertz, this part of the jet with a relatively low magnetic field and emitting plasma number density becomes optically thin. We see it through. We measure its spectrum. We see probably moving components, and this thing we see as the jet origin, as the jet base. So it's the most bright, prominent feature usually in a jet. And so going to higher and higher frequency, we see closer and closer to the black hole. And this effect, the different position, this bright feature is called radio core, and it approximately coincides with the position of a surface with optical depth equal to unity. So for each frequency, to this specific intensity maximum. This optical thickness actually was a problem for Radio Astron. As you know, Radio Astron is our mission where we hope to see, well, not meet, but before, hope to see the black hole shadow. Because of absolutely unprecedented resolution, its orbit was almost up to the orbit of the moon, so it's about 300,000 kilometers. But the frequency range for Radio Astron was 15 gigahertz. So it's like here, and there was no chance of seeing the black hole shadow or looking close to the black hole. And with the Event Horizon Telescope, which has a smaller resolution but higher frequency range, we could detect the black hole shadow at like 43 and 86 gigahertz. So you see that opacity effects are very important, even in planning such a huge missions, cosmic mission like Radio Astron. It's a cosmic telescope. Okay, and let's try to model the core shift offset. What people do, we can observe the position of the cores at different frequencies. We can measure this distance between the cores at the pairs of frequencies. And so by doing this, we can actually learn something about jet properties. The model I want to introduce you is, well, quite simple. It uses the core shift effect, and we assume the following, we make the following assumption to quantify this effect. We assume that emitting plasma has a power law energy distribution, which is more, we assume, despite what I was telling you on the previous lecture, that locally jet is uniform. So when we look at the jet along this line of sight, we assume that this part of the jet is a part of a sphere of a radius capital R, where magnetic field and emitting plasma number density and velocity are distributed uniformly. That was made actually for simplicity, and other approaches need numerical simulations, which we are working on now. So physical values distributed as power loss, also with local jet width. That is important. If we see, if we look at different frequency, we look into another part of the jet, and we assume that this sphere is also has uniform distribution, but with different amplitudes from this part of the jet. So that's a simple model. Why sphere? Because it's quite easy to obtain that for a uniform spherical synchrotron emitting an absorbent source with radius r, spectral flux specific intensity is proportional to the following function of an optical depth. So here is the function. Here are some dimensional coefficient, and T is just total optical depth of this source. So it's 2r multiplied by the absorption coefficient. For this equation can be minimized or rather maximized. You can find a T optical depth which corresponds to the maximum in specific intensity. This is the value for P equal to 2, but you can do it for any distributions. And in order to, this is a very basic equation. And after that, what you need is to evaluate the geometrical local jet depth along the line of sight and rewrite the absorption coefficient in a plasma proper frame. Because that's where we know is the best. We do not want to make a lot of transformations of all these coefficients and specific intensities. So geometrically 2r is equal to this expression. This expression is exact one. Theta is our viewing angle. Usually it may be well bounded, and phi is a jet half opening angle. If we assume the jet is conical. Here I'm telling you about the classical theory, and I will introduce some modifications later. R is a distance from the jet base to this point. So we can generalize this expression because we see that 2r sinus phi is just a transversal jet width here around our line of sight, and later, if we substitute this with this, this expression will be easily applicable even for parabolic or quasi-parabolic geometries we will need later. So our optical depth is equal to this one. Now we need to rewrite it in a plasma proper frame. So D is a jet transversal geometrical thickness, so it's just this line. Plasma goes with a relativistic velocity this way, so which means that D doesn't change when we move into a plasma proper frame, so it's a Lorentz invariant. Optical depth is also a Lorentz invariant because e to the minus tau is just the number of photons absorbed along the line of sight. So when we use counting, it means that it is a Lorentz invariant. So we arrive to this expression, tau is equal to tau star. This is Lorentz invariant, this is Lorentz invariant, and we have to just understand how sine theta star changes with changing the frame, because this is what we needed, the absorption coefficient written in a plasma proper frame. So just to remind you, it's quite easily, this is a like second course exercise, obtaining the aberration effect. You assume your light moves along the line designated by these angles. I put C here equal to 1, and then by using Lorentz transformations, you just obtain that sine theta changes as a Doppler factor. Here is a Doppler factor, Lorentz factor, and classical Doppler factor as a Doppler factor. However, you just obtained the aberration effect. However, when you see the approaching jet, Doppler factor boosts your emission, like boosts your frequency, for example. But we have jets on a cosmological scales, so we need to include a Hubble flow, and Hubble flow carries your jet away from you, and so we need to introduce this factor 1 plus z. Z is redshift. After doing this work, we finally obtain that optical depth is equal to this expression. All these values are written in AGN or in observer frame, and absorption coefficient is written in a plasma proper frame. So using the expression for absorption coefficient and how your frequency changes, so it's again Doppler factor, redshift factor, we were able to rewrite this simple expression in this lengthy and tedious form. And this what we start with in our work. Here is some constant, some constants, observables, and physical values describing a jet and their observational frequency. After that, let us assume that magnetic field and emitting plasma number, density, amplitude are distributed as power laws with indices KB and Kn. And here is just B star 1 is a typical magnetic field at the distance 1 parsec along the jet, and K star 1 is the same, so it's emitting plasma at 1 parsec. Also, generally, we can also quantify Doppler factor, but not in this model. So consider conical jet, constant plasma bulk motion, Lorentz factor. In this case, when you substitute these values in here, you will obtain the following. It's an observational frequency to some power, distance along a jet, so it's a real position, not the projected position along a jet of an observed core in units of parsecs. And here are the observables. Doppler factor is usually measured, redshift, jet half opening angle and viewing angle, and you see only the values of magnetic field and plasma at 1 parsec distance. So what you got here is a constant for a given jet, and so you have R is proportional to frequency, observational frequency, and this index is designated by -1 over Kr, and Kr depends on these particular indices and alpha, which is connected to emitting plasma energy distribution. So you need to somehow find this KB and KN, because alpha is usually measured for a given jet in the optically thin regime. So as we assumed the uniform models, we employ a continuity equation. It's here. And so it means that the plasma number density Lorentz factors are constants proportional to jet width to the power 2. But if we have conical jet shape, then K is proportional to R to minus 2. So Kn is 2. In a jet with a constant Lorentz factor, dominated component of a magnetic field is toroidal. So it's proportional to the total electric current over R gamma. Gamma is a constant. Then B is inversely proportional to R, and KB is equal to 1. So these are classical results, and they are called the Blandford-Koenigsegg scalings, obtained, introduced in this year. If you introduce K and KB, then this expression does not depend on alpha or on P, and it's just equal to 1. So probably that was the reason for such a choice. And actually, for a long time, that has been what is observed in jets. So here is the observational frequency. Here is the separation from some stationary bright feature. This is for this source from the work by Sokolovsky, Italy, 2011. And well, obviously, let me return. Obviously, the jet base is situated at frequency at the infinite frequency. So, so it's pointing right here, somewhere at this distance, the jet base. And here is the result for M87. This KR is measured quite close to unity. So that was nice. And also we can introduce the so-called core shift offset, that's this omega. This is a projected co-position, R sine theta, core shift offset, observational frequency, and core shift index. So here everything except core shift are observables. So core shift is just expressed through two observational frequencies, and here is the projected distance between two cores translated into angular distance in milliarc seconds for the convenience. But on the other hand, these measured from the observations value can be connected with the jet intrinsic properties, K and B. So if we can impose some possible relation between K and B, then we can solve it for example, B, and have an instrument of assessing the magnetic field at 1 parsec distance, so have a feeling how strong the magnetic field is in a jet. So usually the equipartition assumption is assumed, which means that the energy density of a magnetic field in a plasma proper frame must be assumed to be equal to the emitting plasma energy density in the plasma proper frame. So here is the magnetic field density energy. Here is the emitting plasma energy density. We know this distribution. No, it's yes. It's dN, so here is a misprint. So it's gamma over dN, and dN, of course, is expressed through d gamma. So here is And actually we can, of course, calculate the emitting plasma number density by just integrating dn. Here is the expression. It can be different for alpha is equal to 0.5 because we have a logarithm here and not equal to, we have some degree. And we can actually calculate the energy density of emitting particles. And by equating it with energy density of magnetic field, we obtain the following relation. So K is just proportional to B squared, and lambda is usually assumed. Here is a logarithmic dependence. So we do not make huge mistake if we assume gamma max by some one or another value. And so by substituting this into this expression, we obtain the classical expression for a magnetic field estimate by measuring core shift and core shift offset. So here are the results from the very first work. Employed this technique, this work by Lobanov, 1998. This is a magnetic field at 1 parsec in a plasma proper frame, so it's about 1 Gauss. That what we actually expect later. It is corroborated by later, more or less, by later measurements. But we know that most cores are actually lying not in the conical domain, but in the parabolic domain. Here are by black dots are depicted cores, and here this picture, this result is obtained. Here is about the 15 gigahertz core. So mostly cores align in when the jet is parabolic and when a jet is accelerating. And I will skip this. And there is growing evidence that Kr is actually not equal to 1, but has quite a different value. Here is the source 3C454, where Kr has been measured to be 0.78, and this is NGC 315, where we can actually measure 2 branches of core shift for conical and parabolic branch, and for parabolic branch Kr is 0.57, so it's quite far from the unity, and we need to account for that. So what we do is we again retain jet width, but we can assume any jet shape. So if K is equal to 1, the jet is conical, and if K is equal to 0.5, it has a parabolic shape. Non-constant Lorentz factor is proportional to D, so it will affect how we recalculate magnetic field and plasma number density into a plasma proper frame. We use different distance because 1 parsec can be in conical regime, and we assume this power loss. The expression changes because now we have a change in Doppler factor, and for Kr we have a different, a little bit more complicated expression. And now we have to think of the values of Kn, Kb, K delta, and K it just defines the shape. So if the jet is non-conical but with constant Lorentz factor, let's assume it, and Blandford conical scalings, then Kr will be equal to K, not 1, but K. And in different cases, you can estimate actually KB, Kn, and you can obtain that Kr for a smaller viewing angle can be written as follows. And for classical value, L is equal to alpha is equal to 0.5, Kr is equal to K 4/3. So if we have a parabolic shape, K is equal to 0.5, this means 2/3, and it's quite close to 0.66, and that's what actually we observe in many sources. The other option is for large viewing angles where Kr is equal to 2K. So let's, here I just put it, Kr is equal to 0.57, that's quite close to 0.66, and this one has a closer to 2/3 value too. And we can check it actually for two sources, M87 and 3C and NGC 315. So this is a jet shape for M87. We obtained shape index being this value, and from this work Kr is equal to Korolev index is equal to 1.6. So we test all the possibilities, and we see that accelerating parabolic flow viewing at the large viewing angle, which means that Doppler factor would be constant, describes the situation very well, and that's actually consistent with any other M87 models. For NGC 315, we have conical branch, parabolic branch, and we have measured shape indices and Korolev indices, and test all the possible scenarios, and we see that the best scenario for parabolic flow is an accelerating parabolic jet viewing at small enough angle, and conical branch corresponds the best to the conical outflow with a constant Lorentz factor, which supports our modeling of how jets are accelerating. And by the way, it's very nice that by measuring course in this region, we know that we measure the poloidal component of a magnetic field. And this component we can more or less safely extrapolate down to the gravitational scales. In this case, for NGC 315, we obtained by the described method that the magnetic field is around 10 to the 3 Gauss. And for other sources, we have a sample of sources. We have obtained the following values. So more or less, every estimate for magnetic field falls somewhat inside the limit 10 to the 4 Gauss, except for two sources which probably outliers, but that's really interesting. Why? Because if we have a black hole in the center of AGNs, then we know that probably we cannot have a magnetic field more than 10 to the 4 Gauss. But if we systematically have a higher or even much higher magnetic field, then we might suspect that in the center of galaxies there is no black hole, but some exotic object. So that's quite interesting. why it is important to include jet shape into consideration? Because suppose we measure core shift and for two frequencies, so we cannot actually establish core shift index, and if we assume conical geometry, we place some core at some frequency here, and actually if the jet has a different form, we miss it by some distance, which may be important. Now, why is this instrument? I'm just a few last slides. Why is it important? Maybe important for Neutrino. That's because the result by Plavin, when he obtained systematically the following. Well, I will not explain. The picture is obtained quite tediously. But some summary, here is the delay after neutrino detection in years. And here is some indicator for flaring, for jet flaring in radio. So if you look at systematically for many blazars, if you look at the frequency 22 gigahertz, you can see no delay, so your flare comes simultaneously in radio with neutrino signal. However, if you see the data for 11 gigahertz, there is a systematic delay of about 1/4 of a year, which means you receive neutrino, you wait for 3 months, and you see the flaring event in radio in blazar. So this means that, okay, let's use this. For example, if a flare producing neutrinos happens here, then for neutrino jet is obviously always transparent. But the flare, it may be not transparent in the optically thick region for radio waves at a certain frequency. So your flare going through cores and like reaching the core of 11 gigahertz, only at this position, jet becomes transparent for emission from this flare, and you can see this delay. So these opacity effects may be actually an instrument to locate the possible neutrino source location, which may be interesting because in this case you will know the magnetic field there, the plasma number density, which provides you with possible proton number density, and so this I put it as a project, but here is my summary, and I hope this work will be done. I will find a student or a PhD student for this work to complete. Thank you very much, and I'm open to your questions.
Thank you very much for the lecture. Now, questions.
So I have rather 3 questions, and the first one is about, for instance, slide 47. 47.
Sorry?
Yeah. Okay. So, as first of all, I've heard of weather sequence, and that the peak position in the radius part of the spectrum is dependent on the luminosity. And you have said that this peak is also dependent on the energy of the particles at when optical depth becomes unity. So does this mean that this energy, the energy of the particles, depends on the luminosity of the planet?
Well, of course, the luminosity, you will have a different luminosities for different emitting plasma number density. Yes, that's right. You will have the peak going up and down. And also the effect will be the same if, like in flare, you somehow have either a greater or lower magnetic field than in a non-flaring state. So this will affect, of course, the amplitude of the emission. But the position of this brightest feature will depend on an observational frequency and on the internal conditions in a jet.
And the second question is about indices. The star index, what does it mean?
Sorry?
So there was a lot of
stars.
indices.
Oh, I'm sorry. I told, but probably I should do it more. It's in a plasma proper frame. So we have two frames, AGN frames or observer frame and plasma proper frame. And some things like you do not want to recalculate the absorption and emission coefficients into observer's frame.
And you mentioned that we put a lot of parameters to obey the power law.
How correct is it? It is.
Yeah.
Well. We are going to check it. Generally, if we see the most bright part of the jet, then actually we should expect the power law dependence of these parameters. But the best way to check it is to actually calculate the co-positions from the real jet models and to compare it with our estimates, and that's what we are doing now with my PhD student. So this work is undergoing. Why it hasn't been done before? Just because we didn't have an appropriate MHD jet models. They were quite simple. Very simplistic. I know even the models where divergence of B is not equal to 0. So we want to do it only for reasonable MHD jet structure, and that's what's going on.
Any more questions? No one? Then I wanted to ask you a rather simple question. Concerning the main model, you say that the jet is locally uniform along the line of sight, but it seems that we're interested in cases where we look almost right at the jet. So this distance is very large, no?
Well, yes, but actually, we know that. Sorry, I came out. Actually, for the huge majority of the jets, the case of this model actually holds. There is right now just one example of a jet. It's B1424 plus something. There came out a recent paper when you see the picture of the jet when you are looking strictly inside the jet. So it's just one example. It is called, well, they produced a really nice picture. They called it an Sauron eye, and we're also modeling it. But yes, this model would not be applicable to this jet, and that's what we actually observe there, because we see the core shift, and it does not obey this nice power law applicable for other jets. Yeah, thank you.
Thank you very much. Any more questions?
Thank you very much for the lecture. There was a slide with the magnetic fields obtained in different objects.
Here or older one?
Here. I want to ask, are they in the rest frame of plasma or in the observer frame?
No, it is already in the observer's frame. They have been recalculated.
So we can get 10 to 5 Gauss as a maximum.
Well, usually we would expect the sources to be no more than 10 to the 4 Gauss. So 5, either it is some mistakes, some errors in measurements, or it is the real effect. We just need more statistics.
Okay, thank you.
Oh, one more.
Thank you very much for the work. Maybe I just missed it. Can you again repeat what was the frequency for the black hole which were needed? Like in the experiment, you said that it was radio frequency telescope.
Yeah. It's well, 15 gigahertz was not enough, but I can't remember now. I think 86 was enough. Probably even 43. So it's it's apply about 2 or 3 times. That's amazing.
Okay. Thank you.
Okay. Let's thank the lecturer once again.